All right, so the first thing we want to look for is the initial pH. And the initial pH, if you remember, we're dealing with a weak acid to begin with, so we're going to have to do an ice box. Okay, so first let's take our weak acid, which is right there, and let's write the dissociation equation for it. And we know that it's going to make H pluses and F minuses. Okay, now we know we start with 0.1 molar of it, of the actual weak acid, and 0 of each of these. And then I'm going to lose this, gain H pluses, gain F minuses, and that's going to give us X, X, and 0.1 minus X. Okay, so then we set it into products over reactants. You have H and F, so we've got X squared essentially, over reactants, which is 0.1 minus X, and this is equal to the Ka, which is 7.2 times 10 to the negative fourth. All right, now we can cancel out this minus x, so essentially we have 0.1 times the 7.2 times 10 to the negative fourth. So 7.2 times 10 to the negative fifth would be that, and then we would square root that. When we square root the 7.2 times 10 to the negative fifth, let's see, plug that one in. All right, and I get 8.48 times 10 to the negative 3. So it's 8.48. All right, now essentially that's x, and x is the F minus as well as the H plus. Okay, so then if you negative log that, that will give you the pH of the initial solution, which is 2.07. So that's our initial pH that we will need to remember when we graph here in a second. All right, next you want to look at the equivalence point. All right, first let's find the equivalence volume. Equivalence volume is calculated the same way you would have calculated it for a strong acid and strong base. It's just M1V1 equal M2V2. We had 0.1 molar solution, and we use 50 mils of it, and we need to know how much of a 0.1 molar NaOH solution we'll need to neutralize it. So that's going to be 50 mils. Okay, so that's an important value when we go to graph here in a second. All right, now as far as finding the pH at the equivalence point is when the acid and the base have neutralized one another. So we have our weak acid and our strong base, and they're going to neutralize one another and make a salt, which is NaF, and water, which is the HOH. Okay, now because you have a weak acid, strong base, you know this is going to be a basic salt, so you're going to expect a pH at equivalence point above 7. So now we can just go ahead and solve this as if we're finding the pH of this salt. Okay, so we have basically a 0.1 molar solution of NaF salt. Okay, so when we're looking at this, we already know that it's going to be basic, so now we can write the dissociation equation for the salt. So you have NaF, and that's going to break into the Na pluses and the F minuses. Okay, now the one that we are concerned with is going to be the basic form. The basic form is the one who produces hydroxide ions or accepts hydrogen ions. So if you were confused, you could just do both of these, react both of these with water. So you have Na plus with water, and that's going to give you NaOH and H plus. So this is the acidic form, not the one we want. So that tells us that the F minus is what we really need. So we write this out, again, reacting with water. This time we get HF, which means that it accepted a hydrogen, so that's a base, and it left behind OH minus, so there's your hydroxide ions. Now you're just setting up a table, so you know you had 0.1 molar of the NaF, because that was the initial concentration of both of those, so that's going to be your salt concentration. And water doesn't matter in an ice table because it's a solution, a liquid. And then we had 0, 0. Okay, now we know that we're going to lose here, gain here. All right, and then when you do products of reactants, you get x squared over 0.1 minus x, and that's equal to, again, the Ka, which is the, oh, wait, we're wrong. We're not looking for Ka, now we're looking for Kb. So we must find the Kb. So we know that the Ka was the 7.2 times 10 to the negative fourth. So if we do Kw, which is 1 times 10 to the negative 14th, divided by that, that gives us Kb. Okay, so 1 times 10 to the negative 14th divided by that, divided by our Ka gives us our Kb, and our Kb value is 1.39 times 10 to the negative 11th. So this is what we need to be setting our equilibrium expression equal to down here. So we have 1.39 times 10 to the negative 11th, and of course the minus x cancels out, 0.1 it up, and we have the 1.39 times 10 to the negative 12th, and then you're going to square root that to get your x. X is 1.18 times 10 to the negative 6. Now this gives you your OH concentration. So if you do the negative log of this number, that will give you your POH. So when we negative logged it, we get 5.93. So that is the POH. 14 minus that number gives us our pH, which is 8.07. That is indeed above 7, so it is basic, so that's good news. All right, next we want to look at the pH at half equivalence point. Half equivalence point is probably one of the easiest pHs to calculate because at this point the pH is equal to the pKa. Now remember that pKa is basically just the negative log of the Ka. Okay, so when we're looking at this, the Ka is 7.2 times 10 to the negative fourth, so we're going to negative log it. And when we do that, we get a Ka, or pKa, excuse me, of 3.14. Okay, and because the pH is equal to the pKa, we know that the pH at half equivalence is 3.14. Now the volume at half equivalence is just half the volume for equivalence. It was 50 mils for equivalence, so it's going to be 25 mils at half equivalence. So at 25 mils NaOH, the pH is 3.14. Okay? All right, next you would want to look at the pH before and after the half equivalence. You can do this either with an ice table or with the Henderson-Hasselbalch equation. Okay, now to do this equation, you have got to first determine how many moles of the acid and the conjugate base you have. Okay, so first write the equation. So I wrote it in simplistic form, but I wrote it like this. All right, and then that's going to give you an NaA, which is essentially the A minus, and the HOH. Okay, so this is the conjugate base. This is the acid. These are the ones we're worried about. Now, I just picked a point for us to determine. You would have to be able to do the same. I knew that the equivalence point was 50 mils, so before the equivalence point would be 40 mils. Okay, and I knew that half equivalence was 25, so this will be after the half equivalence before the real equivalence point. Okay, all right, and that's going to be 40 mils of NaOH. Now we already had 50 mils of the HA. Now I wanted to find the moles, not the milliliters. I knew the concentration of my acid was 0.1, so that's molarity, which is moles over liters. So this gave me 0.005 moles of the acid. Now, did the same thing with the base, except this time I had 0.04, so now I have 0.004 moles. Okay, so my limiting reactant is this, so that's going to limit how much of the conjugate base I made. So I made 0.004 of the conjugate base. I used all of the base that was added, and then I only had 0.001 moles of the acid left. I then went and plugged these concentrations in, but first I got to get them to concentrations, which means I need the total volume. Total volume is 50 plus 40, so 90 mils, which is 0.09. So I divided both of these by 0.09. My concentration here was 0.011, and my concentration here was 0.044. Okay, so this is my A minus, so that went on top. And this is my acid, so it went there. And I plugged that in, and then I added 3.14, and I got 3.74 as my pH. Okay, and again, we're going to need this in a little while, and that was with 40 mils. Okay, all right, and last one we're going to look at is after the equivalence point. All right, after the equivalence point, we have excess base. So we can basically just look at the base, calculate our moles of excess, total volume, and then find our pH from there. So equivalence was 50 mils, so I picked 60 mils of NaOH because that would mean that I had used 10 mils more than I was supposed to. I had 50 mils of the acid, and that was 0.1, and this was 0.1, so I used 10 mils more of the OH than I needed. So I have 10 mils extra of OH minus. My concentration of the OH is 0.1, and I want to know how many moles, and I had 0.01 liters. Multiplied that across, and I had 0.001 moles. Now my total volume was this plus this, so that's 110 mils, which is 0.11 liters. That gave me a concentration of 0.0091. Now that's the concentration of my OH minus. So when I negative log that number, that gives me the POH. So my POH was 2.04. Then I did 14 minus that number to get my pH, which was 11.96. Okay, now if you go and you plot all of these numbers on a pretty little graph, okay, so this would be 11.96 at 60 mils. So let's see, 60, and then we'll call this about 12. Okay, so we're here. All right, and then we knew that, so let's see, the previous one was, oh, let's see, 3.14 at 25 mils, 3.74 at 40 mils. Okay. All right, so it was 3.14 at 25 mils. So let's see, 50, 40, 30, 20, 10. So 25 mils, 3.14, let's see, 8. Okay. Okay, we're a little off scale here in case you hadn't noticed. So 3.14 is like down here, so ignore that point. All right, and then let's see, we already got this one at 11.96. And then we had 3.74 at 40 mils. So 40 mils. Okay, so just a bump. So this is going to be the buffer region. Our initial pH was right in this range. And then our equivalence was 8, a little above 8 at the 50 mils. Okay, so that would be